Good afternoon and welcome to another episode of the Futures webinar series. Today's topic is one I'm sure many of you viewers will find interesting: synthetic intelligence and nanoscale neural networks. Our guest today is the respectable Professor Zdenka Kunčić, a physicist with a PhD in theoretical astrophysics. She leads an interdisciplinary research program which incorporates physics, medicine, biology, neuroscience, and engineering. Among her many achievements, Zdenka is currently a 2020 Fulbright Future Scholar and an elected fellow of the Australian Institute of Physics. Zdenka, thank you for taking the time to be here and sharing your knowledge with us.
Thank you very much, Enna, and thank you very much also to the Futures Foundation. I'm very honoured and excited to be here, and thank you to Eddie for inviting me. So my talk today is going to touch on a few different areas. It's going to touch on something that everybody's familiar with, surely, artificial intelligence. It's also going to touch on neuroscience and also nanotechnology. And as a physicist, I hope that I'll be able to show you how physics actually can be used to underpin and tie all these different aspects together to give us deeper insight into what the underlying nature of intelligence really is. So you can see from the title of my talk, Synthetic Intelligence and Neuromorphic Nanotechnology, that there's probably a few terms there that maybe are not so clear. So what I mean by synthetic intelligence is something that's quite different from artificial intelligence. So the description synthetic really refers to something that you can make that mimics nature. So when you think of something that's synthetic, you often think of synthetic fibers or maybe synthetic drugs. So something that we can make that is mimicking something in nature. Artificial intelligence, on the other hand, is something that we normally use when we refer to software-based methods that try and mimic some aspects of intelligence. So what I'm going to talk about today is how could we make hardware that produces intelligence? And this is what I mean when I refer to synthetic intelligence. Neuromorphic nanotechnology is the way in which we're able to do this. And the type of nanotechnology I'm going to talk about is quite different from the conventional nanotechnology that most engineers might be used to. So I'll explain a bit more about that as I go through my talk. So I've kind of broken up my presentation into 4 parts. So a background where I'm going to give a little bit of historical context just for motivation and a bit of rationale as to why this is sort of interesting for me at least. And then by way of introduction, I'm going to talk a bit about neuromorphic computing, what that means and what's happening at the moment in this R&D space, lots of exciting things happening. And then I'm going to talk about some of the work that I and my colleagues are doing on synthetic neural networks, which also encapsulate synthetic synapses. And then lastly, I'm going to show you how we use these synthetic neural networks, how we train them and demonstrate learning in hardware. Okay, so just for a bit of historical context, so one of my all-time heroes is Alan Turing, and I think most people who have heard of Alan Turing have heard of him because he is famous for what we now refer to as the Turing machine, which is basically the blueprint for all electronic digital computing that we know of today. However, fewer people know that Turing was one of the first people to start thinking about brain-inspired intelligence. He gave a lot of thought to how intelligence in the human brain emerges. And so some of his early work was really quite different from the subsequent work that he became famous for. He actually looked at something known as the non-deterministic Turing machine, as we refer to it today, that was much more I guess it was quite different from the type of digital computing and the algorithms that we're familiar with today. However, he did work a lot on early forms of algorithms that subsequently led to the development of what eventually became AI. So one of the reasons why some of his early work around brain-inspired machine intelligence kind of diverged towards digital computing is because by the late 1940s and early 50s, the transistor was invented. And of course, the transistor basically ushered in a whole new revolution that enabled modern digital computing. Now, another development that happened after Turing in the 1940s, in the 1950s, Frank Rosenblatt from Cornell proposed this model called the perceptron. And the perceptron was basically a model based on the human brain's neuron. So the individual computational primitive that was proposed to be responsible for the way in which the brain processes information. So that was quite a significant contribution. And then in the 1960s, Marvin Minsky from MIT expanded on that into what is, I guess, is a precursor of modern artificial neural network models. So he proposed a multi-layer feed-forward network, which was basically an expansion of the very early perceptron neuron models. And incidentally, it was already realized in the 1960s that the basic perceptron model couldn't alone do complex computational tasks. So it really needed a network of neuron models in order to do tasks of increasing computational complexity. However, even with that development, by the 1960s, this new research area known as artificial intelligence started to see a decline. And part of the reason for that was because computers at that time were still not very efficient. They were still very clunky, took a long time to process anything. So the very early artificial neural networks that were developed in the 1960s were very, very difficult to implement computationally. So I guess they were just too early in terms of the relative to the technology that was available then. However, by the 1980s, the situation improved. So computers became a lot faster, a lot more CPU power, and so some of these early ideas around artificial intelligence started to gain traction again. And then there was another significant development in the 1990s. Carver Mead from Caltech coined this term neuromorphic engineering. So what he actually proposed was this idea that electronic systems could actually be engineered to operate like the brain. So if you like, silicon neurons. However, some of his early ideas were also very reminiscent of Turing's early ideas. And you probably won't be able to read this whole paragraph directly, but in this paragraph, he actually points to the idea of analog signals as being more important than digital signals if we really want to try and emulate the way in which the brain works. And in his last sentence is kind of quite insightful as well. This kind of adaptation leads naturally to systems that learn about their environment. So this idea that we need to build into these new electronic systems the ability to adapt to changing input signals. That's what really motivated him. I'm going to come back to this idea of neuromorphic engineering that Carver Mead first proposed, because there's been some really interesting developments around that in the area of neuromorphic computing that I'll touch on in a little while. But before then, to continue our little historical journey, so in 1997, we saw the first demonstration of what we now refer to as deep learning. And that was when IBM Deep Blue actually beat the chess grandmaster Garry Kasparov. And that was really a phenomenal milestone in AI at that time. And of course, since then, we've seen so many more amazing milestones that AI has been able to achieve. However, one of the key challenges that AI faces is an ability to move beyond a single task. So AI is really, really good at very specific tasks, like playing chess, like playing Go, like doing image recognition for a particular class of images. But once you train an AI model to do that particular task, it can't do anything else. If you want it to do something else, you need to start from scratch. So in AI research today, the holy grail is this idea of artificial general intelligence. How can we create new AI models that can really generalize, that can really do computation across multiple tasks? So I've just listed here some of the differences that I see between what we currently refer to in terms of machine computation, whether it's machine learning or AI, as compared to the way in which humans think. So the first clear difference is really that machine learning is very deterministic. So if A, do B. Whereas the way in which humans think, the way in which our brains work is not like that. The way in which we think is more like if A, do B, or you could do C, or you could do D, or E, or F. So there's a lot of non-determinism in the way in which humans think. And of course, every single brain is different and will give a slightly different answer for a given task. So the second difference is also accuracy and also, I would say, precision. So machine computation is a priori designed to give a single accurate answer to high precision. And that's quite different, again, from the way in which the human brain works. The human brain has a whole range of possible outcomes. And that part of that is the way in which we describe the creativity of the human brain. A third difference is between machine computation and human thinking is the repetitiveness of machine computation. So machine learning and AI are really, really good at repeating instruction after instruction after instruction, so brute force computation. We can never do that. We would find that so boring. Conversely, what we're really good at is adapting to changing environmental stimuli. And lastly, another point of difference is that machine learning, at least the way in which we implement it today, is done in a very static way. So we collect a whole bunch of data and a lot of data, but that data is static. And the way in which we implement our algorithms is such that it learns on that static data. We do all this offline training and then we deliver another set of data based on the task at hand. And that's quite different from human thinking. Our brains are able to process information in a very dynamic way. The data that we are constantly receiving from our sensory inputs is dynamically changing, and we can adapt to those changing inputs. So the challenges that this holy grail of artificial general intelligence face are really big challenges. And it's not yet clear that the existing approaches that are used in AI can be continuously developed along the same path in order to get us from machine learning to human thinking. So it might well be that we need to think of a completely different way in order to achieve AGI. So it's also interesting that a lot of the developments in machine learning and AI have really come from computer science. More recently, there's also been a lot of developments from the engineering disciplines, and I'll talk a little bit more about that in a moment. But very little has really come from neuroscience up to date. Now, this abstract is from a paper that was published in 2017, and part of the collaboration here is from Google's DeepMind. And this paper is really about this idea that, oh, hang on, if we really want to realize artificial general intelligence, then maybe we should start to look at neuroscience. So neuroscience is really coming into this quite late in the piece. So it'll be interesting to see how the AI community starts to incorporate this enormous wealth of knowledge that has been gained from neuroscience research. So I want to talk a little bit now about neuromorphic computing. So the word or the adjective neuromorphic just means brain inspired. So there's something brain-like about the way in which this computing is done. And neuromorphic computing today generally refers to neuromorphic chips, although there are some other references that can be made here as well. But certainly neuromorphic chips, which are chips that now have an architecture that is described as beyond von Neumann. So they integrate the processing and memory together. And one of the big motivations for doing this is because the power consumption drops by orders of magnitude. So a number of companies now have their own neuromorphic chips. And one of the reasons why they're developing these new chip architectures is in order to implement different AI models. So many of you may appreciate that training AI models is actually probably the most hardest thing to do because it's very, very computationally intensive. And so these models are very power hungry, particularly in training. So these chips are designed in order to make AI training a little bit more efficient. Now, what's interesting also is that the way in which neuromorphic computing has evolved in, let's say, the last decade is really starting to look like a realization of Carver Mead's original idea when he proposed this idea of neuromorphic engineering. That is, can we develop new types of electronic systems that are starting to mimic the brain? So this diagram looks a little bit busy, but let me just walk you through it. So this diagonal line going through the middle here is meant to represent power. And all these pictures are images of different types of chips. So the IBM's True North chip that I just showed before is down here, as is Loihi as well. And then up here, closer to the high end of the power spectrum, is the sort of area where we'd find our average desktop computer chip operating at. Whereas a little bit down here is the power at which the human brain operates. So it's thought to operate at about 20 watts or so, comparable to a light bulb. And there's a few other chips here as well that have been developed recently, neuromorphic chips. So there's Spinnaker and brain scales, which I'll talk a little bit about here. So these are neuromorphic chips that have been developed by the EU's Human Brain Project. And again, the goal here is to develop neuromorphic chips so they're a bit more brain-like. They integrate CPU and memory, so they're operating at very, very low power. But they're a little bit different from chips that have been developed to implement AI algorithms. So the idea here is to use the chips themselves and get the chips to actually act like the way in which the brain does. So it's more like training the hardware directly rather than implementing additional AI algorithms on it. So this is really now starting to get quite close to the vision that Carver Mead originally had when he coined the term neuromorphic engineering. So engineering brain-like chips that can actually operate like neurons in the brain. So really, really exciting developments that have happened in the last decade or so. So now I'm going to move on and talk about a completely different approach. This approach is really motivated by trying to see if we can develop brain-like intelligence from systems beyond silicon and CMOS. And the reason for doing that is because we know that the brain isn't made of silicon. It's a biological system, And so the way in which it's made is quite different from the way in which we make things in engineering. So what I'm going to first talk about is this idea of, okay, well, we know that when we make chips, we use nanotechnology, but we also know that if we're interested in this idea of general intelligence, how can we try and produce the type of intelligence that the human brain has? We know we have to look to neuroscience. And so let's try and marry these two aspects together, the neuroscience and the nanotechnology. And for me as a physicist, physics underpins both of those aspects. So there's a lot of really interesting physics and dynamics that's going on in the neuroscience of the brain. And of course, physics also underpins nanotechnology. From neuroscience, we know that the brain works as a complex physical system. So it's not a piece of software, it's actually a piece of hardware. So that's an important point that we need to keep in mind all the time. And we also know from neuroscience that the brain's function, all the cognitive function that neuroscientists study, are intricately linked with the structure of the neural network. And that complexity gives rise to emergent phenomena. So in other words, a lot of the cognitive abilities of the brain arises as emergent phenomena from this complexity of the neural network structure. So that's the first piece of information and clues that we get from neuroscience research. Now, the second bit of information that we get from nanotechnology is a little bit different from the nanotechnology that I've been talking about so far. So when we talk about chips, for example, these are made using top-down fabrication techniques, so lithographic fabrication. But half of nanotechnology involves bottom-up synthesis, and this is the sort of thing that chemists do. Now, we also know from biology, when we're thinking about the brain, that all of biology actually creates complex structures from what's something known as bottom-up self-assembly. So if we use that type of nanotechnology, the bottom-up synthesis type of nanotechnology, as opposed to the top-down fabrication, then in principle, we should be able to make nanotechnology structures that are more bio-like than they could be if we use top-down fabrication. And because bottom-up self-assembly also generates structures that form naturally, if you like, they form natural structures as opposed to very rigid, highly designed structures that are made from top-down fabrication, then we should be able to see quite different functionality from those two approaches. And so the type of structures that I'll be presenting now is a structure that's starting to look like a neural network-like electronic circuitry. So here's a scanning electron microscope image of one such structure. And this is made from nanowires, and we call it a neuromorphic nanowire network because the network does look quite brain-like. And we also call it neuromorphic because the way in which this structure is made is from bottom-up self-assembly. So these nanowires are made from silver, and they're made in a wet lab. They're not made in a clean room facility. You can make them in an afternoon. And you basically bring all the ingredients together and let the nanoscale structures, the nanowires in this case, self-assemble. Now the structures are nanowires, so all these stringy things are nanowires. They're nanoscale in one dimension, in the cross-sectional dimension, where they're typically maybe 5 to 10 nanometers across. But their lengths are very, very long, so they can reach up to maybe 100 or 200 microns in length. So they're very long and stringy. Now, because these structures are nanoscale in one dimension, that means that they have unique physical properties that emerge as a result of that geometric confinement in that dimension. And in this case, we have very unique electrical properties that these nanowires exhibit as a result of their nanoscale structure. So I'll talk about that as well, and how we can exploit their unique electrical properties to turn these networks into really interesting electronic circuits. So as I mentioned, these nanowires self-assemble into a really complex and a really highly interconnected network with a topology that's really similar to a biological neural network, as you can see by comparing these two images here. Now, because the nanowires have interesting electrical properties, we can actually stimulate the network. And when we do that, we find that the junctions between the nanowires, where they overlap, act like electrical junctions in a very similar way to the way in which the junctions or synapses between real neurons work. So on the left-hand side here is a little cartoon that shows you what happens between two neurons when there's a synaptic connection. So an action potential starts the stimulation, and that triggers the release of neurotransmitter molecules from one neuron to the other. In a similar way here, the electrical junction between a pair of nanowires looks like the following. The nanowires are silver, but they're coated in an insulating polymer. And so where they overlap, there's a metal insulator metal junction. And when there's an electrical bias there, when you stimulate the network, what happens is that you get silver cations migrating from one side of the nanowire across the insulating layer to the other side. And eventually you actually get a conductive bridge that forms across them, like so. What this does is it forms an electrical switch. So that junction switches from being in a low conducting state or an off state to an on state, where it suddenly becomes very highly conducting. And that's really interesting, this switch-like behavior at the junctions, because when it's in a network structure, we get really interesting adaptive dynamics that we observe as a result of all the switches at all the junctions responding in a self-regulated way. So let's have a look at this structural details a bit more, because neuroscience tells us this is really, really important. So on the left-hand side, there is an image of a nanowire network. And this is presented in what's known as a graphical representation. So all the little red dots you can see actually correspond to nanowires, and we call them nodes, whereas all the white lines correspond to the junctions, or in graphical representation, we refer to them as edges. Now, these nanowire nodes and junction edges, you can see that how densely connected they are. And that's really important as well, because in the brain, we know that there are about maybe, 100 billion neurons. And maybe, each neuron has maybe up to 10,000 synaptic junctions. So that scale and density of neurons and their synaptic connections is really, really impressive. And it's actually quite difficult to achieve that in a typical artificial neural network model. So if we look on the right-hand side here, there's a schematic diagram of a multi-layer artificial neural network model. So there's an input layer, an output layer, and in this case, there are three hidden layers in between. And each one of those nodes in each layer is meant to represent an artificial neuron. And you can see also that the neurons between the layers are also connected to each other. So they're meant to represent the edges in this diagram. But what's more important is that the graphical structure of artificial neural network models used in AI is completely different from the type of complex topology that the brain has. And so one of the really interesting research questions that we're addressing is how much does that network topology play in terms of the type of intelligence and computational tasks that can be performed by these networks. So again, referring back to neuroscience, so a lot of neuroscience research comes from different types of measurements. So for example, there's EEG data, there's a lot of in vitro experiments that are done on real neural cells, but there's also a lot of work done in functional MRI. And functional MRI is really important because it tells us something about how the function of the brain is connected to its structure. So a lot of researchers in neuroscience, and a lot of them are physicists, are now looking at these different network topologies, ranging from a random network, which has no structure, through to other types of networks that have some very specific structures. And what has actually emerged, and I think a consensus is that this kind of intermediate type of network topology known as a small world network appears to be the optimal type of topology for efficient communication and efficient information processing. So that's what we've learned about from neuroscience research. So we've started looking into that for our neuromorphic nanowire networks, and it turns out that because these nanowire networks are self-assembled, the self-assembly process naturally produces a network topology that is small world. So that's really interesting, and it's also, so that's shown in this green diagram down below. And moreover, what's interesting as well is that that type of small world topology is completely devoid from artificial neural networks that are used in AI models. So again, we're really asking this question around, well, how does this small world topology give us better efficiency in different computational tasks for these type of nanowire networks that we are interested in? So one of the ways in which we're studying these nanowire networks is where we're also modeling them. So we've set up a computational model to better understand how they work, and also to optimize their design so we can make improved versions of them in the lab. So there's a couple of aspects that need to be considered in modeling them. So the first aspect is modeling the electrical junctions. So the electrical junctions vary with time. So I've already mentioned that the junctions can switch from an off state to an on state, and that evolves over time according to the actual time varying input bias that's applied. So we can apply pulses, we can apply different types of input electrical stimulation and biases, and look at how the junctions evolve with time. So we have a specific model that models this switch state for the junctions. And the second part of the modeling refers to the topology of the network. Now, we need to obey Kirchhoff's laws, so the current laws and the voltage laws, and this now needs to be applied in a very complex network circuitry. So again, this is quite different from a standard integrated circuit that you might be more familiar with in electrical engineering. So we're able to do this by using an adjacency matrix that encodes all the structural connectivity of the network. And then once we've modeled both the network and the electrical junctions, we can look at a whole bunch of different responses of the network to different electrical input signals. So what I'm showing you now is just a simulation of a very simple network of nanowires, and you can see a little bit of switching going on here. So all the little circles represent the junctions in this network, and all the lines represent nanowires. And in this case, we're just applying a DC bias from the number 1 electrode node up the top down to the number 2, which is grounded. And so some switches, some of the circles you can see changing color. So this represents switches changing from being off to on. And you can also perhaps see some white arrowed lines, and this represents current passing from one junction, through one junction, along the nodes to the other one. So thereby you can actually see how the current pathways evolve over time through the network. And importantly, it's the network itself that determines the optimal pathways for transmitting electrical signals. The right-hand side plots just compare the network conductance that we measure experimentally to that which we predict from our model. So we've studied the switching behavior at the junctions a little bit more closely, and this diagram just shows you a snapshot zooming in on what's happening when the very first current path forms across the network. And it clearly shows that happens when you get junctions that have switched on that are close to each other and therefore able to transmit currents across the network. And this is quite important because this is one representation of what we refer to as a collective effect, when you get a whole bunch of individual elements, the junctions in this case, that act together to create a system level response. We can also perform other types of analysis. So in this case, this is a power spectrum of the conductance time series that produces power law power spectrum. And these type of power spectra are also seen in functional MRI brain data as well. Now, another really important property of these neuromorphic nanowire networks is something referred to as collective memory. So in this plot here, I show you in black the conductance time series of the network in response to a series of pulses. So these are voltage pulses at 2.5 volts. And you can see that once the voltage pulses are switched off, the conductance of the network actually persists for a period of time afterwards. And we refer to this as memory. Now, what's also really interesting is depending on the way in which we pulse the network, the way in which we feed in the signals, we can actually achieve different types of memory. So now you can see that the pulses have extended for up to 10 seconds, and the network is able to retain its state, in this case, its conductance state, for a longer period of time than the first example. So this shows you that there are clear differences in these states that the network can attain in terms of its memory properties. So in this case, we have short-term memory and long-term memory. And these are also two very important memory states that are observed from neuroscience research. What's also important about collective memory is that this is absolutely essential for being able to achieve adaptation across different computing tasks. So one of the reasons why AI models are not able to generalize to different tasks is because they suffer from something known as catastrophic forgetting. In other words, they're trained to do one task, but if you move them onto another task and train them for that, they'll completely forget the first task that they learnt. So this memory property is absolutely important in order to generalize learning. So here I'm showing you some experimental results, and these experimental results were conducted by collaborators in Japan. So on the left-hand side, you can see a little schematic diagram of a nanowire network, and the nanowire network is actually it's stimulated, and then it's being imaged in the infrared. So on the right-hand side, you can see two panels of infrared images, both in amplitude and phase. And the way in which this analysis is done is electrodes are placed on either side of the network, and we can control which electrodes are open and which are closed. So we can actually control the pathways that the network establishes in response to the input voltage that's applied to the network. And in this study, we were able to actually demonstrate how the network is able to remember previously established pathways and how it can use those previously established pathways for future, to access in future stimulations. Similarly, these are other experimental results demonstrating training in hardware, and in this case, pattern recognition. So again, the network is now connected to electrodes, input electrodes on the left and output electrodes on the right. And we can train the network to remember specific pathways. And then we can subsequently test the network to see to what extent it can remember specific pathways. And with these multi-electrode arrays, we can then create different types of patterns of input and train the network to recognize those patterns for pattern recognition tasks. Now, one of the really important properties that these neuromorphic nanowire networks possess is something known as recurrence. So recurrent feedback loops means that it's quite related to the memory property of these networks. So the network is able to have these nonlinear feedback loops that allow it to remember states that it was in at earlier time points. And this turns out to be absolutely crucial to enable adaptive dynamics, and also allows the network to sustain its own internal activity without additional inputs. So we've examined this particular property to apply it to different types of learning tasks. And this is, again, really, really different from artificial neural networks used in AI models, where the synaptic weights are continuously being iterated on in order to train the network. Here, the network is not trained, it adapts itself to the changing inputs. This is the last example I wanted to show you. It's an example of a signal processing task. So the plot here shows you is a plot of voltage versus time, and the signal that you see here is a signal called the Mackey glass signal. It's a really well-known signal because it has chaotic regimes, so regimes where the signal becomes very unpredictable, and that's the regime that I'm showing here. So if you look at it, it kind of looks like it might be quasi-periodic, but it's just going into this chaotic, non-deterministic regime in this particular case. So this is a really key task for a lot of information processing approaches, because if you can predict a signal that is, essentially unpredictable, then that tells you there's something really interesting that this particular system is capable of doing. So what you see in this plot for the first, I think it's 15 seconds shown in blue, is the input signal applied to the network. And the network is trained to recognize this signal. And then after that, the input signal is stopped, and the network then self-generates that signal. And the self-generation of that signal is shown in red. You can also see there from 15 to 50 seconds that there's also some blue parts. Now, in this case, we had to remind the network of the signal, because it turns out that there were errors in the way in which the network predicted this signal. And because this is a chaotic signal, those errors amplified exponentially. So we needed to inject reminders to the network of the signal that it was required to predict. and this is actually quite an important task that a lot of systems fail upon. With this particular technique, we were able to achieve an accuracy of 98%, which is actually pretty good. I just wanted to finish up with a couple of applications. I've spoken a lot about these networks, and they seem really cool, but what can they do? So one of the things that we're kind of thinking about is this idea of a synthetic neural network on chip. And so once you've got these nanowire networks on a chip, in principle, you could then use them for a whole range of things. So our main interest lies in their potential application in autonomous systems and Internet of Things sensors and devices that are at the network edge. And this is really where all of IoT technology is going nowadays. So we're already using mobile devices, but wearables are coming in. We've got autonomous vehicles that are coming onto the market. Our homes are going to have electronic devices that are completely interconnected. So all these kind of devices and the associated sensors that they use are all operating at the network edge. And in some cases, the edge is either very weakly connected to the internet, to the cloud. So it's quite difficult to send data back and forth to the cloud to do processing. So if you think about it, if you're in a remote location, or if you're in a situation like a hospital where privacy is of concern, you actually would prefer to be at the edge or disconnected from the cloud. But there's an even more specific example, which is called the extreme edge, and that's in space. So space is receiving a lot of attention. All satellite technology is by definition at the edge and often referred to as at the extreme edge. It's not connected to the internet. There's no terrestrial or it's limited terrestrial connection. There's no cloud there that you can send data back and forth to. So in that particular context, we absolutely need to have systems that cannot rely on big data, labeled data, doing processing offline. So we need to be able to have a new generation of systems that can process information that's continuously changing in time and doing that processing on the fly. So this is one of the key application areas that we're very much interested in. And one final application is a biomedical application. So a very good colleague of mine who's a biomedical engineer has actually developed a bionic eye, and actually looking to see if we can replace the existing chip in that bionic eye device with this kind of synthetic neural network chip to see if that will enable the retina to improve image reconstruction by the brain and thereby improve the image that the vision impaired person is actually able to achieve. And this is mainly designed for people who are almost or entirely blind. So I'll just quickly summarize on this one page two key, I guess, take-home points that I hope you can take home with you. So the first one, which is just a summary, is this idea of synthetic neural networks. So these are physical hardware systems. They're not artificial neural networks in software. And most importantly, they contain synthetic synapses. And the synthetic synapses are key because they actually do all the information transmission around the network. With a synthetic neural network, we have the potential platform for next generation, what I call synthetic intelligence on Internet of Things technologies. And the second point is really an outlook for what I call beyond AI applications. So looking at anything that's on the edge, looking at robotics and autonomous systems more broadly, the extreme edge in space, and also potentially neural interfaces. I mentioned the bionic eye application, but once that's demonstrated for one neural interface, there are plenty of other neural interface type of applications that would ensue as well. So I've come to the end of my talk, and I just want to leave you with this one last slide to dwell over. I'd like to thank you very much for your attention, and I look forward to your questions. Thank you very much.
Thank you, Zdenka. So the first question we have is actually from Eddie. He's asking, can you provide more insight into how the neuromorphic nanowire networks are grown in the lab?
Yes, so they're made in the chemistry lab, and basically once you know the ingredients, so we make them with silver and a particular type of polymer. So there's a very well established experimental protocol that allows you to then you mix all the ingredients, and for particular temperatures and pressures that you use to actually create the nanowire structure. So those are the requirements for particular nanostructures. And then you can create the nanowires in solution, and then you drop cast them onto a substrate. That substrate can be glass, it can be a ceramic. Those are the two main substrates that we work with so far.
And the next one is, looking at the industry roadmap of synthetic intelligence, in your opinion, when can we realistically expect to see the full commercial application of this research?
Wow, that's a great question. So I guess I'll need to be a little bit speculative here, but also optimistic. I'm always optimistic. So I think there are some key application areas. The one that I'm most interested and excited about is this one in space. There's been so much investment in satellite technology, and yet the data analytics, it really lags behind there, because currently all our data analytics is focused on machine learning and AI in the cloud, and that's just not possible. So at the moment, the very limited data analytics that is done with data that is being collected from satellites is actually being downlinked back onto Earth, and it's being analysed there. Now that's very inefficient, and it also becomes impractical as more and more data is being generated. Another development that is happening in that space, pun intended, is that we're moving rapidly from static images being generated by satellites to videos. And really, this is the trend for everything. Everything is going to become streaming data. So no more static, photos, images, everything is going to be streaming. And I suspect that sometime in the near future, we are going to have so much streaming data that we're not even going to bother to store it anymore. We are just going to process it and use it on the fly, and then that's just going to continue. So we will still have data centers. There will still be a need for big data, but streaming data is really going to become more and more important.
Wow. I'm trying to process all of the information right now. So another question we have, is this R&D mainly done at universities and academic institutes, or IT and other companies are involved as well? And if yes, at which level?
Yeah, so we're doing a lot of it at the University of Sydney, but we also have a very strong collaboration with the National Institute of Materials Science in Japan. So they're very focused on the nanomaterials side of things, and the functionality of those materials that we work with the nanowires in this case. We also have a collaboration with the California Nanosystems Institute at UCLA. So that's the main sort of academic collaboration, if you like. And we are also trying to attract interest from industry partners. We have some in-house expertise on the computer science and neuroscience aspect, and of course I'm coming in from the physics side of things. We've had some interest from companies, but I guess it's early days yet. But we're very open to that.
Okay, we are getting more questions now. The next one is there anywhere we can get the formula? The self-forming network looks pretty cool, and I would like to see if I can play around with it.
So not yet. So obviously, I haven't divulged everything yet, but hopefully we will be able to share some more information in due course.
And can you tell us more about the new discovery at Fero?
The new discovery at, sorry, I didn't catch the last bit.
FERRO.
I'm not familiar with that. So
ferroelectricity in hafnium oxide and phenomena of nanoscale.
Okay. Yeah, okay. So as I briefly mentioned, whenever you shrink something down to the nanoscale, even if it's just in one dimension, it doesn't have to be 3-dimension. This is the whole reason why everyone is interested in nanotechnology and nanoscience, is because you suddenly observe interesting new phenomena emerge, phenomena that material didn't exhibit in the bulk scale. So some of those phenomena are interesting optical properties, some of those phenomena are magnetic, some of them are electric, and so in some cases you can have a material that, might not be magnetic in the bulk scale, and then all of a sudden it becomes super paramagnetic on the nanoscale. Likewise with electrical properties. So you can have a material that suddenly has really interesting ferroelectric properties once you shrink it down to nanoscale. So I'm not overly familiar with the hafnium oxide ferroelectric properties, but that's the general principle, that basically a lot of people who are working in nanoscience, nanotechnologies, shrinking things down onto different scales and different structures and observing these new physical properties that emerge on those scales. And then obviously trying to think about how they can use those new properties.
And how do we help younger generations better understand the importance of interdisciplinary research approaches? As humans, we are too stuck in our silos and fail to see beyond our own disciplines.
Look, I love that question. Thank you for asking it. As you can see from my bio, it's something that I've practiced. I did a PhD in astrophysics. I loved it. I still, really enjoy that topic. But as a physicist, I feel like physics is everywhere. So I feel like I really am in a position where I can understand lots of different problems from the training I've had as a physicist. And I feel like I'm in a unique position to do interdisciplinary things. The biggest problem that I've experienced in this is that not everyone is able to think in an interdisciplinary way, and not everyone is interested either. So you have to find the right people who are willing to meet you in the middle somewhere, because the biggest barrier is language. Different disciplines have different languages, they have different terminologies for the same thing. You might be talking about the same thing, but you describe it in different ways. And so you really have to find the right people who are willing to, who are just as interested in it as you are, and who are willing to meet you in the middle and make something work. That's not easy to do, and it does take a long time. I'm at my university. I also am a lecturer, so I teach students, and we have an opportunity to get them involved in research projects. So I try and introduce scientific problems rather than a particular type of aspect of physics that they're going to become an expert in. Because once you have a problem you're interested in, then you think, what do I need to learn to solve that problem? And, it's not going to be just you, it's going to be other people's input coming into that as well. So that's my experience.
And what is an advice you would give to anyone that wants to enter this industry or switch over from a different one?
I think just be open. I think one of the reasons why, look, it's really exciting that we're seeing nanotechnology and neuromorphic engineering and AI kind of converging. But it's also frustrating because you can see, and I can see this from my perspective, that each contribution has come from its own discipline area. The computer scientists don't talk to the engineers don't talk to the neuroscientists. So I see this as a huge opportunity for someone who is willing to learn all of these things and bring them together. I'm trying to do that a little bit, but there's more that can be done by other people as well. So if you are a young person and this area interests you, just think about how you can think outside your own box and bring together these different disciplines into some kind of intersection where you will have an advantage because these other areas, they're only thinking in their own little comfort zone.
And a related question, any advice for young STEM professionals in Bosnia and former Yugoslavia? How do we create success here by leveraging knowledge of our diaspora, which includes yourself?
Yeah, another great question. So I would say don't hesitate to ask people for help. Honestly, I wouldn't have gotten to where I am today without many, many, many people helping me. And I think you'll be pleasantly surprised at how many people who are, more progressed in their career are willing to help people who are at the start of their careers. So you should definitely think that people are more likely to help you than not, so you shouldn't hesitate. Just go for it.
At the moment we don't have any more questions, but something that I've been really curious about when it comes to these kind of combination type projects, is it easier to gain IT related knowledge when you have a natural science background, or is it easier to kind of build up the natural science knowledge when you have an IT background?
Oh, I think definitely the former. So as a science student, and particularly in like physical sciences, and maths, for example, all the way through you learn about coding and how to simulate something, so it's kind of comes with your training. But I think if you start from IT, it's very difficult to learn about how you do science. It's hard to learn about a specific discipline of science, whether you do biology or physics or whatever. So I think it's much easier coming from science because you're already exposed to methods that are used in IT, and if you need to know more, you already know a little bit about it, so you feel like you can learn more if you want to go deeper.
Well, thank you so much. I'll conclude with two comments from our viewers. The first one is, thank you for making me stop regretting the signal processing classes I took this semester. And the second one is from Eddie. Thank you, Professor Kunčić. You're brilliant. I am 36 years old and I am deeply inspired by your work. You're a great ambassador for women in STEM, Australia and former Yugoslavia.
Oh, thank you so much. Thank you very much. I appreciate that comment. And thank you, Eddie, for inviting me and for making me aware of this really fantastic foundation. So thank you to Ina. Okay.
Well,